My name is Gillat. I do theoretical computer science, mainly complexity theory. I graduated from the Weizmann Institute, and I'm happy to be here. And I'll be talking about interactive channel capacity, and this is joint work with Ran Raz. And this doesn't work. Oh, on and off, good. Okay, so you know, probably one of the most influential paper in science is this beautiful result, this beautiful paper by Claude Shannon from 1948 named A Mathematical Theory of Communication. And in this paper, Shannon shows an exact formula for channel capacity of any noisy channel. So let me talk about this result. Okay, so we'll consider the epsilon noisy channel. This is a binary channel, and it flips every bit with probability epsilon. So if I send 0 over the channel, then with probability 1 minus epsilon, I'm going to get the output 0. However, with probability epsilon, I will get a 1, and this is an error. And then we consider the following setting. So assume that Alice wants to send an n-bit message to Bob. So 2 people, right? How many bits does Alice need to send over the epsilon noisy channel? So Bob can retrieve with probability almost 1. So by almost 1, I mean 1 minus little o of 1. Okay, so basically, if we're talking about the noiseless channel, Alice just sent her n-bit message to Bob, and she's done. However, if we consider the epsilon noisy channel, we probably need more bits, right? We need some redundancy. But how many more bits do we need, right? So it's not even clear that this blow-up here is constant. So you can repeat the message. You can send it times and times again. But then you may need to send it, say, log n times in order to correct all the bits. So can you even do it with a constant blow-up? So this is one of the beautiful results by Shannon. And Shannon shows that the number of bits you need over the noisy channel is n over 1 minus h of epsilon. And h of epsilon is just the entropy function. It is given by this nice formula. And note that not only that Shannon shows that the blow-up is constant, but he can pin down the exact constant, which is kind of impressive. And he kind of does so by showing a matching upper and lower bounds. And this number, 1 minus h of epsilon, which is of course smaller than 1, is called the channel capacity. It's kind of the discounting factor of the channel. And basically, if you get a bit out of this channel, then this bit morally contains only 1 minus h of epsilon bits of information. So you got less than 1 bit of information because of the noise. So this was Shannon, and let me tell you about what we do. So we're considering a related question, the question of interactive channel capacity. So again, we have our guys, Alice and Bob, but now they want to have an n-bit conversation. So before we had the case where Alice just preaches to Bob. She just tells Bob stuff, and Bob doesn't respond. But now they talk. And again, we ask how many bits do they need to send over the epsilon noisy channel so that they both can retrieve the transcript with probability that is close to 1. Or again, what is this blow-up here? And I just want to mention that interactive systems, just systems where a few parties talk in order to achieve a goal, kind of model real-life scenarios, and these are really widely used in theoretical computer science, in complexity, in cryptography, and so on. Okay, so next I want to formalize the notion of interactive channel capacity. I'll give you a formula for that. But first I need to tell you what communication complexity is. Okay, so again, we're in an interactive setting. We have Alice and Bob. And now Alice has an input x, and Bob has an input y. And they wish to compute a function of both inputs. So they want to compute f of x, y. So we assume that f is known to both Alice and Bob, and that it takes 2 inputs and returns something. Okay, and then the communication complexity of this function f is the least number of bits Alice and Bob should exchange, should communicate in order to compute f of xy. So now that Alice can just send her bits to Bob, but this may be costly. Maybe she can send less, right? Maybe they can communicate less bits. So there are several notions or definitions for communication complexity. One is the deterministic communication complexity. I'll denote it CC of f. And here we want that for every x and y, the players will be able to compute f with probability 1. So this is the least number of bits the players should communicate in order to compute f of xy always, with no error. And then we can consider the randomized communication complexity. I'll denote it RCC of f. And this is a relaxed version. And here we only ask that for every xy, the players will be able to compute f of xy with probability that is close to 1. So they're allowed to make errors, but they need to be correct for every pair of inputs with high probability. And we'll be allowing them to share a random string. So there is kind of a sequence of random bits that they can both see and use it to kind of synchronize. And the last notion that I'll mention, and this is a non-standard notion. This is the notion we use in the paper. And I'll denote it CC epsilon of f, the noisy communication complexity. Again, we want the same guarantee for every pair of input, compute the function with probability close to 1. However, now the players communicate over the noisy channel. So first two definitions are standard, and they're over the non-noisy channel. And last one is kind of the one we're using, and it's over the epsilon noisy channel. Right. So now I'm able to define the interactive channel capacity. And the interactive channel capacity is given by this formula. OK, so just to remind you, CC of f is the deterministic communication complexity. CC epsilon is the noisy communication complexity. And let's try to parse this thing. OK, so first note that this n here, here, and here is just the regular communication complexity of a function. And let's look at this mean part of the formula. And this mean part asks how small can the ratio be between the communication complexity of a function and the noisy communication complexity of the function. So basically, this mean part looks for a function f that has a rather small communication complexity, but if you introduce noise, then the noisy communication complexity is high, relatively at least. And then you take infimum over the communication complexity. So basically, you look for the worst case family of functions. I just want to mention, to remark that the result will hold if I replace the CC here by the randomized communication complexity. So you can use deterministic or randomized, result hold. And if you know what's worst case versus average case mean, you can use either a worst case definition or average case definition of communication complexity, and everything holds. Good. So let me tell you what was known before. So if you forget, this is the channel capacity, and this is the formula. Previous work. So over 20 years ago, and Schulman shows this nice theorem. He shows that if the non-noisy communication complexity is n, then the noisy communication complexity is at most O of n. And by O of n, I mean that there exists a constant alpha that is independent of the parameter n, such that the noisy communication complexity is smaller than alpha times n. So this is what Schulman shows. And a corollary is just that the interactive communication complexity is greater than 0. That's what you can immediately get. And then Schulman asked, well, is it possible that the interactive channel capacity is just the channel capacity? Can those be the same? And he that this is unlikely, right? Because interactive channel capacity is maybe smaller, right? Because in the interactive case, if you have an error in the first bit, it may cause the whole conversation to be totally meaningless. So if Bob didn't understand the first bit sent by Alice, then he may talk nonsense from now on. So maybe this is harder. OK, so I'll show you our results. And this is the first and kind of the main theorem we have, and it's an upper bound theorem. And what this theorem says is that the interactive channel capacity is at most 1 minus omega of square root of h of epsilon. So again, what this omega means is that there exists a constant alpha, which is independent of the parameter epsilon, such that interactive channel capacity is at most 1 minus alpha times square root of h of epsilon. And as you can see, for small epsilons, we get a separation. We show that the interactive channel capacity is strictly smaller than the channel capacity. And just to remind you, this was the channel capacity. So for small epsilons, we do get a separation, and we answer the open question by Schulman. OK, so this is an upper bound result, and we have a kind of a matching lower bound. And this is the lower bound. We show that the interactive channel capacity is at least 1 minus O of square root of h of epsilon. And again, this O means that there exists a constant, say beta, such that the interactive channel capacity is at least 1 minus beta of square root of h of epsilon. And beta, again, is independent of epsilon. And we show that for the case where the players take alternating turns, or you can generalize for any case where the pattern of turns is kind of periodic. So those two are kind of matching up to the constant here. Those constants may be different. And the model is not exactly the same. So they're not exactly matching, but, you know. OK, so I just want to say something about the proof. So this is kind of the hardest thing here. And we need to show that the interactive channel capacity is smaller than something. So to do that, we show an explicit example of a function such that the noisy communication complexity is, you know, substantially higher than the communication complexity, and then this ratio here is small. So we kind of show such an example. And of course, the hard part will be to lower bound the noisy communication complexity. So usually to give a lower bound for something is hard, because you need to show that no protocol does better, right? And here it's especially hard. It's especially challenging, because usually when you show a lower bound, it's up to constants. And here we need to know the constants, and we need to know the second order terms even. So you need to do a really fine, careful job, but we do it. And to show the second result, so the second result is easier, and you need to show that the capacity is greater than something. So what you do is you construct a simulating protocol, an algorithm. And this algorithm just takes any protocol, communication protocol that works over the non-noisy channel, and shows how to simulate it over the noisy channel without using too many extra bits. OK, so this is our result. And that's all I have.
Thank you very much.